Okay.
For the first five, you gave us the hint of it requiring the unit circle, it,
Okay.
requiring unit vectors. I assumed you were referring to the unit circle. Somebody else did it from physics where they found the normal force and then split it up.
Okay. Whoops. Wrong one. So remember that the unit circle, all that stuff is giving you unit vectors to any point on the circle, you know? So those really are the same thing. I don't remember this problem yet. So we are on particle statics.
It has us find the force in between the ground and the surface.
This one?
And friction. Yeah.
Oh, okay. Right. Okay. So okay, this thing is at rest. Okay. Uh, do you have a version that says something about the unit circle or something?
Yeah, for part B, it's.
This is not right.
Oh, was there another part to this one below the? I think there might be another part on the
Yeah.
next page.
Oh, really?
Well, I think your question is more about that last part, right?
Yeah.
Okay.
Not necessarily the whole problem.
Yeah. We just.
Does it ask you to split it up into?
Yeah, into
Okay.
the normal and the friction.
Okay. It looks like that's an old version, maybe.
If I remember correctly.
The normal forces applied to the block.
Okay. All right. So
And basically, you just have like enough information to figure out what the normal is, and then if you already figured out the total.
okay. So watch this. This is like magic. Okay. So we're gonna. Okay, we're gonna say part C. Split it up into a normal component and a parallel component. What the? Where'd my stupid dumb thing go?
There's some sort of
Gremlin?
well, it keeps doing that to me too. It minimizes all the windows on that.
Oh. Huh. Okay, so we're going to split it into normal and parallel components, you know, perpendicular and parallel to the surface. I don't know if it's part C or what, but okay, so Jesus Christ, what the hell is going on? Okay, so free body diagram. I'm going to just go through it all. The early stuff is quick. So we got this block. It's the angle is 20 degrees. We have a 50 Newton force like this. We have a weight force of 20 kilograms times 9.81, so 196.2 down. And then this is a friction contact. So the rules for friction contact are an unknown force vector. We don't know either component. I'm just going to call this R. And then that's it for the free body diagram. So Newton's second law says this R I'm going to call Rx, Ry. We don't know either component. So I'm first just doing it in this coordinate system. And you can actually tell that by the way I drew my unknown force vector, because you're always drawing those in the directions of your coordinate axes. Okay. And then we got 0, negative 196.2. And then negative 50, 0. And this is at rest, so there's no acceleration. And the two equations then tell us that Rx is 50, Ry is 196.2, and so altogether this vector is 50, 196.2. Okay? Okay, so this is part A. Part B, we want to know what's the force that the block applies to the incline. This is the force vector that the incline applies to the block, right? And so Newton's third law then says, so you could write this as the force on the block by the incline. FBI! Don't move! And so that means that the force on the incline by the block, Newton's third law says that's equal to negative FBI. Okay? And so this is equal to, just multiply that by negative 1 and you get negative 50, negative 196.2. You want that to just become like very natural, like your hands do it by yourself while you're watching Dukes of Hazzard or something, you know. If you switch those subscripts, you switch the signs. Okay, and then the one we're here for is part C. Now, how do you break this up into normal and horizontal components? So you could do it by finding projections and stuff. That's how you would have had to do it in Physics 1. But now I'm going to do it with a rotation matrix. Okay, so we want to go from this coordinate system. That's the one that we have our components in, to a coordinate system like this. So how do you have to rotate the coordinate system on the left to line it up with the coordinate system on the right? Theta is equal to, so the incline is 20 degrees, but you also have to think about the direction. Remember, counterclockwise is positive. This is negative. This is clockwise, so it's negative. Negative 20 degrees. Okay? And so our rotation matrix is cosine of negative 20, sine of negative 20, negative sine of negative 20, okay, so it looks like that. If you want to think about it, you can, change stuff based on even and odd functions, but you might as well just plug it into your calculator. There's not too much engineering point in analyzing it any more than that. So this will come out to be 0.866, negative 0.342, positive 0.342, positive 0.866, and so our force on the block by the incline in the new rotated coordinate system is equal to 0.866, negative 0.342, positive 0.342, 0.866, times what that vector was in the old coordinate system, which was 5196.2. Okay. Negative 23.80 180, that's not an 8, 187.01. Okay, and so our coordinate system is, this is now a vector in this coordinate system. And so we have a horizontal component like this and a vertical component that's much bigger, I don't know, like this. And so the total is this. Any questions about that? So this isn't something, I think really this is on the homework because I was hoping to show you that, and so everything worked out according to my plan. I don't think, that's not something that I'm going to make you do on homework or anything, but later on in this class, you'll be using those matrices more. Yes?
When we give our final answer, would we not need to turn it back to its original coordinate system?
This is the answer. So the answer, I guess, is, it's answering the wording of the question. So what's the force vector? Oh no, split it into normal and parallel components. So it would be like that force, the one parallel to the surface is 23.80 going this way. And the one perpendicular to the surface is 187.01. These are in newtons going this way. I guess that would be the best way to answer it. But you wouldn't want to, if you re-expressed it in the old coordinate system, it would have made all this pointless, because your answer would be 5196.2. Do you know what I mean?
Yeah.
So we just put it in a new coordinate system, and then to put it back in the old coordinate system would bring us back to where we had been. Anybody want to talk about this more? Any questions about that? Eventually, the goal is for this to be a very natural thing to do in your head, do these coordinate system transformations in your head. In D form, it's going to, it'll be very natural for you. We'll do it all the time in 3 dimensions instead of 2 dimensions. But right now, I'm just kind of trying to get you used to the idea that this thing is out there somewhere, Any other homework questions you want to see? Everybody's like, no, I wish we didn't even see that one.
Well, I don't know. I guess but we could have, like you said, done the projections,
Yes.
found the horizontal
Right.
component of that 50.
That's right. That's right. But when you're used to this is a million times faster, So, once you have it, you have a program in your calculator, so you just go, okay, the rotation is, so we're transforming from this to this, so the angle is -20. You plug into your program -20, it pops out the matrix, you multiply times this vector, and it's done in 20 seconds or something,
I'm just wondering why I got the wrong answer.
Oh, well, let's do it with projections. So, okay, so we have a vector. Okay, so we know our starting projections. Okay, so we know that our starting vector is 5196.2. And we're going to just take a dot product of that with unit vectors parallel and perpendicular to the surface. Okay, so a unit vector parallel to the surface. And it doesn't matter which, I mean, you can do it with either one of the two vectors parallel to the surface. You know, if you look at the, so you could have a unit vector going this way or one going that way. So I'm going to do one going like down and to the right. So that unit vector would be 0.866, negative 0.342. That's cosine and sine of 20 degrees, negative 20 degrees. And so the projection is 50, 196.2, dotted with 0.866, negative 0.342. And so that's 50 times 0.866 plus 196.2 times negative 0.342. Bless you. And so that is negative 23.80, you know, which matches what we got.
Yeah.
And then perpendicular to the surface, that would be an x component of, so now I'll do the one up and to the right. So that is positive 0.342, positive 0.866. And so we got 50 dotted with 50, 196.2 dotted with this 0.342, 0.866. And you get 187.01.
Then I did it as a series of equations,
Mhm.
and cosine sine plus friction sine over sine.
Yeah.
cosine.
Uh-huh. And did you get the same thing? Okay, yeah, right. Yeah, you can definitely kind of think it through geometrically, and if you do it right, you'll get the same thing. But the fastest way to do it by far is once you're comfortable with that rotation matrix, and it just spits out the two answers for you at once.
Thank you.
Mm-hmm. Okay. So we are talking about moments. And I gave you the equation last time that the moment about the point A is equal to the row vector crossed with the force vector. And that row vector is defined as the coordinates of the place where the force is applied minus the coordinates of the about point. One thing that is useful about this, especially in 2D, a little less helpful in 3D. It just sort of takes more thinking to use. But the right-hand rule for moments. So think of a force acting on a body. And an about point A. Okay, so that about point, think of that as like a hinge or a ball and socket joint that the body is rotating around, able to rotate around, okay? And so I'm going to go back to the bolt and wrench example. So the wrench is the body. Let's say that we're applying this force F here. And now think about, think about the direction that this thing would rotate if the only force on it were this force. So if F were the only force, which way would the body rotate around A? Okay, this is A is here. Okay, so in this case, it would rotate counterclockwise. And so the right-hand rule says, curl your fingers in the direction of that rotation. And then the thumb is in the direction of the moment vector. Okay, so in this case, your fingers would be like this. And your thumb would be out, like pointing out of the page. Like that. Okay, so the fingers are curling around in the direction of the rotation, and the thumb is coming out of the page towards us like this. And so the moment vector here would be, the moment vector would actually be like if the coordinate system was x to the right, y up, z coming out, it would just be a positive z moment. Okay, so let's see how that works in a calculation. One thing I'm going to, we're going to use all the time in this class is as a bookkeeping thing, is we're going to use this table. And so the columns are going to be row vector, force vector, moment vector. And this is going to be, each row is going to be an individual force. So let's do it for the example we just did. Okay. So let's say that this force is 800 newtons. Okay. Let's say that this length here is 0.2 meters. Okay, and let's calculate the moment. It should be in the positive z direction. We're going to use a coordinate system like this. Okay, so let's fill this out. The row vector, that's the vector going to where the force is applied from the about point. So that's going to be negative 0.2 in the x direction. Are you with me on that? Does everyone see that? Does anyone see that? So this is going to be negative 0.2, 0, 0. The force vector is in the negative y direction at 800. So this is going to be 0, negative 800, 0. Okay, now take the cross product. If you cross out the x components, you get 0. So there's no x component for this moment. If you cross out the y components, you get 0. So there's no y component. So the only one is going to be the z component. Cross out the z components, and you get negative 0.2 times negative 800 minus 0 times 0. And so the moment is 0, 0, positive
160.
Oh, yeah, right. Yep. 160. Okay. In 2D, eventually, just to save time and stuff, since we know it's only going to be a z component for the moment, we're gonna just write out the x and y components of the row and f vectors, and then just report this as a z component only. But it is useful to remember that that moment is always a vector.
So when you say each row is a force, so if you had like 5 people pushing on the same wrench.
Yeah. So when you do a free body diagram, you'll have like 5 forces on a body or whatever. You'll have 5 rows. Mm-hmm. And then the benefit of that is every, so you'll have this, and then it'll keep going. And then when you're done with that table, all of the forces that go in Newton's second law are there. So these add up to give you Newton's second law. And all of the moments for the moment equation will be here. I'll call that rotational Newton's second law. So that right-hand rule, it works in 3D. You can always think of it that way. It's just a little harder to visualize in 3D usually, you know. Okay, let's do one more example with this table. This time, well, let's do it in, let's just do a 3D example. So let's say that we have the coordinates where the force is applied. I'm just going to make up numbers. Negative 20, negative 35, 10. Okay. The about point, let's say that's negative 5, negative 12, 2. And then the force that's being applied at that point P is 600, 1200, negative 1500. What's the moment produced by that force? Well, the row vector for that force is, it's always just equal to P minus A. So this is 20, negative 35, 10, minus negative 5, negative 12, 2. And so that's 25, 47. Oh, no, it's not. 23, negative 23. And then 8. And so now I'm going to set up the table. Row, force, moment. The row vector is 25, negative 23, 8. The force vector is 600, 1200, negative 1500. You could spend a while doing this by hand, or you can, and you get a moment of 24,900, 42,300, and 43,800 Newton meters. Yep.
Y wouldn't be negative?
I did not get that, but did you do it by hand or? Okay, so remember that when you do the cross product by hand, yes, exactly.
Stupid Y.
Stupid Y, exactly. It's always trying to screw you up. So trying to do that using the right hand rule and whatever would be just a nightmare on stuff like that, but just plug it into the cross product.
I would have been happy too.
Yeah. Okay, so let's start making some more physical examples. So let's say that we have a two-dimensional shape like this. Our about point is going to be here. And we have a force of 10,000 newtons this way. And at that same point, an upward force of 20,000 newtons. And give some dimensions. Let's say this is 0.5 meters. And this is 2 meters. What's the moment produced by that force? And we'll use like a standard coordinate system. Okay, I'm going to pause this, and why don't you take a few minutes, couple minutes, and so I'm going to just set up this table. This table really doesn't, I mean, I suppose it might help you organize your thoughts a little, but it's really going to be a lot more helpful once we just have multiple forces. But for now, it's just sort of getting used to it. Okay, so the row vector, that's the vector that goes from A to where that force is applied. So that is an x component, a positive x component of 2, a negative y component of 0.5, and then 0. The force is positive 10,000 for x, positive 20,000 for y, and then 0 for z. And then for the cross product, it's 2 times 20,000 minus negative 0.5 times 10,000. So that's 40,000 plus 5,000, so 45,000. And the units are Newton meters.
A lot of force.
It's not force. It's like torque, you know. So
Well,
remember,
it's
but
still-
that's a hell of a lot of torque. Like, does anyone have a feel for how many? I mean, I think the people who are used to calculating torques with torque wrenches or whatever, like you're used to different units than Newton meters. But anyone have an idea? Like, say with just a regular screwdriver, if you're cranking as hard as you can, how many Newton meters can you generate? Somewhere in the ballpark of 10. So yeah, that's a really, really big torque.
I'm just thinking about like climbing equipment and what that's.
Oh,
you know, like
yeah.
like maybe 40 kilonewtons or something. We're
Right.
to take a fall from like 30.
Oh yeah. Well, yeah, but just remember that's a different kind of thing than a force. But actually, you can produce more newtons of force with muscle force, you know, than you can produce torques generally. I guess it depends on how big your moment arms are. You're right, it's very big. And we could have also written this as, just write this as 2 negative 0.5. Since this is just in the plane, write this one as 10,000, 20,000, and then write the moment as 45,000, because we know it has to be the z component. Just remember as you're doing this, that really represents the component of a vector. These moments are always vectors. Okay?
Does that have any kind of physical meaning?
Well, yeah, I mean, the direction of it tells you the direction of rotation it would cause. Yep. Using the right-hand rule. And, you know, the size tells you how likely you are to turn that thing. Like if you're trying to turn an object, the moment will tell you how much angular acceleration you'll get or how likely you are to get it to start, no matter what force and what moment arm combination you
Yeah, I
use.
guess it's just weird.
So yeah,
It's weird to think of it like pointing.
it is weird, but that's going to be a really common thing. You can always think of the right-hand rule as a connection between some kind of rotation and a perpendicular axis, you know? And so all rotational things, like there's no such thing as a rotational vector, you know, there's no such thing as a circular rotating vector. Vectors are only arrows. And so any rotational quantity, its direction is going to be with that right-hand rule relationship. Yeah. Angular, like in physics 1, maybe they talk about it, but you don't tend to really dwell on thinking about it that way, angular velocities and angular momentums and stuff. But if you see those as vectors, it's always the right-hand rule thing. Yeah.
So it'd be fair to think of it like a definite integral where it adds up each point into a single line, and that's how much force was put on it at all the different points.
Explain that again. I've never thought about it that way, I don't think.
Like a definite integral
Yeah.
where you've got your radius of your circle, you're adding this spot plus this spot plus this
Uh-huh.
spot plus this spot all stacked up on that single z-axis.
I'm not sure. I don't see it yet, but maybe. I might ask you about that later. Any other questions? Okay. We probably are not going to get to any homework for today. I might give the first weekly assignment. I'll think about it. But let's just start another example problem in the last 5 minutes. So Okay, so let's do a 3D one. And so let's say we have a plate. And you can imagine it connected to the wall by hinges. And let's say that the dimensions are this length is 2 meters. This length is also 2 meters. Doesn't look like it, but. And we'll call this point P. And then 1 meter up the wall here is the connection for a cable. And so a cable goes like this. Okay, that P is at the center. Is it exactly the center? And I'm going to use a coordinate system with its origin here. So I'll make this the x-axis. This the y-axis. And then this the z-axis. If the cable tension is T, what's the moment the cable force produces about A?
So you say there's hinges on the wall?
Yeah, although it doesn't come into it yet, but I mean, if you're just trying to visualize what this is, like this thing is, connected to a wall.
In a non-rigid way.
Yeah. Otherwise, you wouldn't need that cable. Well, it would be redundant, but sometimes you might use it just to reinforce things. Okay, so how are we going to do this? How are we going to do this? Maybe we'll just talk about how to do it right now, and then we'll do the calculation on Wednesday.
The coordinate system?
Yep, got the coordinate system, so we're done with that part.
So so 0, 0, oh, it's at the left.
Yeah.
Over there.
Right. And so, yeah, so the cable tension is this unknown T, but we can come up with the direction of this cable force because we know it's parallel to that cable away from the chosen body. So we know that that force vector is pointing from P towards, let's give this a name. So this is the point A here, and this is, call that B. Okay, so what we're going to do to find that force is we're going to find the coordinates of B, find the coordinates of P. Okay. The row, no, it's not the row vector yet. But we're going to calculate a vector that goes from P towards B by just taking coordinates of B minus coordinates of P. Okay. Will that be a unit vector? No, not yet, but we can make a unit vector in that direction by dividing it by its length. Okay. Then we'll multiply that by T, and then we'll have a vector that has a magnitude of T and it's in the desired direction. Okay? Then we'll need the row vector. The row vector, remember, is P minus A. So we'll find the coordinates of this center point. The coordinates of A in this case are 0. That's just where we chose the origin. That'll give us row, and then we can fill out that table row and calculate the moment. Anybody have any questions about that? If you have a minute, like I said, I'm not assigning any homework. I might have a problem or two, but I don't think so that you're ready to do yet. But if you have the time, see if you can calculate that, and then I'll do it at the start of class on Wednesday. Okay, that's all.